Hi, this is a non-relativistic approximation of a particle decay problem. So the original problem is that there is a particle of mass m, and it decays into two particles. One has one half of the original mass, and the other has 1/4 of the original mass. So we scan this equation and explain what happens. So based on the conservation of energy, this 1/2 is just part of the kinetic energy equation, and this 1/2 is 1/2 the original mass, and v is the velocity of the first particle, and similarly 1/4 is 1/4 of the original mass. Okay, I don't have to do the calculation. Let me go back. W represents the velocity of the second particle, and here we have the rest energy of the first particle and the rest energy of the second particle, and because the conservation of energy, they all add up to the energy before the decay, which is the famous E equal to mc squared. So now let's solve the problem. So the first thing we can do is we can pull out m, because there's a m in every term. We can pull out this m, we factor out the m. Now we can move m to the other side of the denominator. That becomes denominator. And one up, one down, same m, they can cancel. So m cancels. And now notice all these terms has a c squared. Looks like they can cancel too. They can be factored out too. So let me move all of them to the other side of the equation, and we factor them out. Good. Now we can do the calculation. Okay, 1 minus 1/4 is 3/4, minus 1/2 is 1/4. Okay, now let's look at the other side. I can calculate these numbers, so to get rid of them, and we can simplify this even further. I can move this to the other side. That becomes 4. We distribute the 4 into the two terms, remove extra parentheses I don't need, and now I can do more calculations. They multiply to 1, and they multiply to half. At this point, I have done everything I could done, and I need to use the second conservation law, which is conservation of momentum. Since we use a non-relativistic approximation, we can show that we can easily know that the mass is twice of the other one, so the velocity is half of the other one, or in other words, W equals 2v, and we can do the substitution here. W equals 2v, and we don't need another W there. Let's do the substitution. W is replaced into 2v. Now we can do the calculation. We distribute this 2 into the base. I don't need the parentheses. 2 squared is 4. That becomes 2. Now I have 2v squared there. I can factor them out. 1 plus 2 is 3. Move 3 to the denominator. Square goes to the other side. That becomes square root. Okay, I can simplify this a little bit. Here the square and the square root, they cancel, so that leaves me with only c, and I can move c to the other side. Okay, that's the answer. Square root of 1/3 of the speed of light, without relativistic consideration. We can leave it as it is, or we can even turn that into numerical numbers. That'll be this, and that's the velocity of the first particle, and obviously the second particle is just twice of that. Thank you.